Hello everyone, this is Mainak, your civil bro. So today we'll understand about seismic loads from the very basics and we'll solve a practical example in theory as well as in STAAD. So our goal is to understand the various codal provisions of the seismic code as per the IS 1893-2016, which is the latest code as per the date of the video I'm recording, and we'll understand this and we'll compare the results of the base shear of the manual calculations with those results of the STAAD.Pro. So without wasting any time, let's get started. So let's start with it. And this is a seismic load calculations, and I'll also provide the study material in the description with the help of a PDF or any other format. You can download it for free. Okay, so what are the seismic forces? So basically, all we understand about seismic forces is that when earthquake comes, a force acts on the building. So now these are predominantly horizontal forces, so they act on the building in the horizontal directions, but in some cases you need to also consider the vertical component of the earthquake. Okay, so the vertical component of the earthquake needs to be considered as per the 6.3.3 of the IS 1893 part 1 2016. So all the code provisions which I'll show you are of IS 1893 2016. So what it tells us, so you should design the vertical component of the earthquake if the structure is situated in zone 4 or zone 5. This is the first criterion. Or it has plan irregularities, means if the building is irregular, or it rests on soft soil. Translation, if you have pile foundation, then it means that you need to consider the vertical earthquake effects, that is 2HVC. Okay, so if you design bridges, if a structure has long span, say span of 10 meters, 12 meters, or those kind of structures, and if the structure has large horizontal overhangs, means if you have large cantilevers, then obviously you have to design or consider the vertical earthquake effects. So for any important building or any building lying in zone 4 or zone 5, we need to consider the vertical earthquake effects. Okay, so what does the IS code tell us? What are the two methods of the seismic analysis? One is the equivalent static method, and the equivalent static method is used in structures of zone 2 of height less than 15 meter and time period of 0.4 seconds. So what are the zone factor, zones, all we will understand. No need to worry, time period, everything we'll understand. So just know for now that for time period less than 0.4 second and for zone 2 we designed by equivalent static method. Now, what is the dynamic analysis method? The dynamic analysis method needs to be used in all buildings more than 15 meter in any zone. Whatever the zone is, if the building height is more than 15 meters, then you need to incorporate the dynamic analysis method. So we'll not discuss about dynamic analysis method in this particular video. We'll go here by equivalent static method. Now there is also a concept of crack sections which you need to apply as per clause 7.4.3. The moment of inertia for columns is to be taken as 70%, and for beams it is to be taken as 35%. So in RCC buildings, when we design, only the 35% of area of beams is considered in the X and Z direction, and for the column 70% area is taken. Reason being, when earthquake comes, if the structure has some minor cracks, then the entirety of the section will not be available to protect it. So we consider this a percentage of the strength. Okay, so you need to consider this crack section property along the X and Z. Okay, so now moving on to the problem statement. We'll understand every concept in detail. Just this is a problem statement. So we have a basically a 3-story building here, and the story height is 3 meters, as you can see. The bottom story height is 1.9 meter, and this is a very simple span, 5 meter, 5 meter spans and 6 meters span in this direction. Okay, so you can see this is the case here. Elevation and section of this very pretty simple. And for the section properties, we will apply 300 mm and 300 mm for all the members, and this will be an apartment building. Location is in Agartala, Tripura, and this location will be used for seismic zone, know later. And then the building type will be RCC. Okay, and the building loads will be, dead loads are given, typical floor loads are given. For typical floors, that is except for the terrace floor, all the other you can see, so all the other 1, 2 and 3 floors, the dead load will be 12, and only for the terrace floor the dead load will be 10, and live load for typical floors will be 3, and for the terrace it will be 2 kN per meter square. So this is the problem statement. Now let's look at the solution along with the concepts. So static analysis method incorporates very simple formula which you can find in clause 7.6.1, which is the base shear. So base shear is equals to horizontal acceleration coefficient into the seismic weight of the building. So this is what it comes to. So we need to find out, if you need to find out the base shear, we need to find out first of all H, the horizontal acceleration coefficient, and the seismic weight. So we'll understand the seismic weight first. So how the IS code has defined the seismic weight and how we calculate the seismic weight. Okay, so seismic weight, if you can just look into the clause number 7.4.1, the seismic weight is full dead load plus the appropriate amount of the imposed load. Okay, so what is full dead load? We have to take, that is granted. Now what is the approximate amount of dead load? So then for that you go to page 20 of the IS code, in which the table number 10 is given, and in table number 10 it tells that if your live load is up to 3, then you take 25%, and if your live load is above 3, then you take 50%. Okay, so we take in the seismic weight the full dead load and a percentage of the live load as per table number 10. Now there is another clause which is important to the discussion of the seismic weight of the building. As per IS code clause 7.3.2, for calculation of seismic forces on buildings, the roof imposed loads need not be considered. So the imposed load you can take for typical floors anyway, but for the terrace floor or the roof of the building, you do not need to consider the imposed load in the seismic weight. So that's an important aspect of the seismic weight calculation. Okay, so how to calculate the seismic weight? Now floor area, here if you just look into our plan, so it is actually 20 meters into 18 meters. Okay, so this was our floor area. So 20 into 18 is our floor area, which is 360 meters square. Now the load which you have on typical floors, dead load which you have on typical floors is 12, and on terrace is 10, and in the seismic weight full will be taken, so factor is taken as 1 for both the dead loads, and the respective dead load for the typical floor is 12 and for the terrace floor is 10. Area is same for everything, and number of floors in the typical floors is 3. Okay, and number of terrace is obviously 1. If we multiply this, we get the weight of the 3 floors and then the terrace. Similarly, in the live load, the factor will be 0.25 because the load is up to 3. The factor should be applied as per table number 10, which is 0.25, and the load comes as 0.75. So 0.75 multiplied by the area and into 3 number of floors is 810 for the live load typical. Okay, and for the terrace, you need to consider 0 because the IS code recommends that there will be no live load considered in the terrace. So total typical floor seismic weight is calculated. We add this and this, and total terrace floor seismic weight we just add this. So if we add these two, the total seismic weight of the building comes as 17370. So this is the total seismic weight of the building. Remember that we ignore the self weight of the building. So in STAAD.Pro also, when you do the design calculations, we'll ignore the self weight of the building. Okay, like this we'll get the accurate results. So next comes the time period. So why the time period? Time period has not been mentioned in this formula. You can see PV equals to AH into W. We just know what is the value of W. We not need to know AH. So for knowing AH, we need to know time period, because without knowing the time period of the building, we cannot know AH. So let's look forward to calculating the time period for this building. By the way, you can take the notes for this building, and you can use for any project, any assignment, and or even for practice. This will be very helpful. So practice along with me. Okay, if you require, you can pause, and if you have any queries, you can just drop it in the comments. Okay, so time period is required for finding AH in the horizontal direction X and Z. So now let's talk about X and Z first. X and Z axis in the STAAD.Pro, as you can relate to in this first slide. You can see X and Z in the STAAD.Pro are the axis, horizontal axis, and the vertical axis is Y in STAAD.Pro. By default, you can change that, by the way, but by default X and Z are the horizontal axis and Y is the vertical axis. Okay, so when it comes to this, let me just go back to this. So when it comes to X and Z, we have our IS code clause number 7.6.1 C for all other buildings. Earlier there are two other options for RC structural walls, which we will not use because our building doesn't have RC structural walls. Another one is for RC buildings without any masonry infills. Now many people do this mistake and use that option. Do not use that option because we having masonry infills or bricks in our structure. So we will be using this option. This is the correct option for all other buildings. TA is equals to 0.09 h. H is the height of the building and root over d. So height of the building, if you calculate if we calculate, we have 3 plus 3 plus 3 plus 1.95, total is 10.95 height of the building, and in x direction the distance is 20 and z direction distance is 18. How we found that? Just you go back, if you have in doubt, go back, 5 plus 5 plus 5 plus 5, 20, and in the z direction 6 plus 6 plus 6 is equals to 18. So we found the area like this. Now TA into x, simply put the values, 0.09 into 20 divided by root over 0.09 into 10.95 divided by root over 20. You find the TAX value and TAZ value. So both the values you can find 0.22 and 0.23. So now you found the TAs. Now for the horizontal acceleration coefficient, which we need for the base shear formula, AH. Now for the AH, we need the first of all, what to do with the time period formula. So time period we got written in this. So you can see for the static equivalent use, as per the table here in the same page, in page number 9, you will find for equivalent static analysis, SA by G, you can see from C, that is Z by 2, SA by G, R by A. Z is the zone factor, R is the response reaction factor. Again, let's see everything here, and I is the importance factor. Everything we'll discuss, don't panic. Okay, SA by G value here for equivalent static method and for medium stiffness soil, because in the earlier problem statement we found that we are using medium stiffness soil. For all time period values of less than 0.55, the SA by G value will be 2.5. So SA by G is short at 2.5. So remaining Z by 2 and R by I we need to find out. So let's find out that. So as we are building location is in Agartala, as per the map, seismic zone map given in page number 11 of the code, Agartala lies in seismic zone 5. So if Agartala lies in seismic zone 5, then as per table number 3 given in page number 10, the zone factor is 0.36. So Z by 2 comes as 0.36 by 2 is equals to 0.18. So another one sorted, Z by 2. So now we need to know R and I. Okay. So R I will find in the table number 8 of page number 19. So for buildings less than 200 occupancy, or that is all other buildings, we need to take an importance factor of 1. If our apartment building has more than 200 occupancy, then we can take 1.2. If the building is an important building like any crucial hospital or any public buildings, then we should take 1.5 as per table number 8. And the response reduction factors. Now, when you are doing the earthquake analysis, especially in seismic zone 3, 4, 5, then we consider ductile detailing. So we only consider ductile detailing, we have to consider special moment resisting frame. And for the special moment resisting frame, as per table number 9, our response reduction factor is 5. So R is 5, I is 1. So all of these values we take together, okay, TX, TA, Z we already know, and so that's why SA by G, Z by 2 is 0.18 and R by I is 5. So by putting all this in this particular formula, we have all these knowns, we get age x and age z is equal to 0.09. So now if the time period were different, then SA by G might be different, and might be in a different range, and this value might also be different, but in our case this is the same age value for both the horizontal accelerations. So we found the horizontal acceleration coefficient. Now what about the vertical acceleration coefficient? So we'll find that clause in clause number 6.4.6 in page number 14. So vertical acceleration coefficient is for the buildings governed by IS 1893 part 1, which we are currently following. So this should be 2 by 3 into Z by 2. So Z by 2 already know, SA by G will already this in SA by G is not required directly 2.5, we can take this according to this formula, and R by I is 5. So AHY comes as 0.06. So if you put in this particular formula, BB is equal to AH into W. So W is fixed, this is equal to the building. AH is a percentage of the weight which you will take. Okay. So the percentage can be more, the percentage can be less. So if it is 6% in the vertical direction and it's 9% in the horizontal direction. So whatever multiplied by this, we get the value of the base shear. So 0.06 into W. W is the same for all the directions. Only the age value is different. So vertical direction it is 1042.2, and for the horizontal directions it is 1563.3. So this is the horizontal load direction and vertical directions base shear calculation. So now we have to do the base shear calculation in STAAD.Pro. So whenever you are using STAAD.Pro, make sure we do the proper settings. So for that, go to configure and make sure your unit is basic unit set to this metric, and you can just choose any color for this format. And in this you can go and change the design code. So if you changed it to your country code, so for example I've changed this concrete code and steel code to the IS code, so the by default the IS code will come, and the by default the units will be my SI units which I want. So you can change this and then you can start. You need to change this only once. For all the projects you will find this. Okay, so you click on new, and we just click on, just give a name here, structure 23, and we'll just create the projects here. Okay, so now since our structure is pretty simple, we'll use the structure wizard here. So here go to click the structure wizard here, and here select the frame model. So you use the bay frame option. Okay, double click, and here bay frame option has come. So length is always taken in the x direction. So in the x direction our was 20 meter 4, and in the y direction it was 18 meter, and number of this was 3. Okay, and along the height number of bays were 4, and the height was 10.95. okay, 10.95. so now for this it will be evenly distributed, which we want, and this also evenly distributed, which we want. But for the height we want different arrangement. So our base bay height was 1.95, and then all the 3 bays comes as 3 and 3. Okay, and click on OK. So now this adds as 10.95, and click on apply, and you can see the model has been ready here. So we don't need to check the units because already we have set the units to kilonewton, but if you are not configured you need to check the units from here. Okay, I can see and select units, and you can check the units. Okay, I've configured so that I don't need to check the units here. So I'll go to file and merge model to STAAD model, and yes and 0. So this my model is ready. Next I'll give the properties. Okay, click on properties and then click on define. So I received a comment to just slow down my tutorial. So I'll just try to slow down for now. Okay, so 0.3 and 0.3, and click on add, and then close. So now you click on this, and we find the option of assign to view, and then assign to all the elements here. So once you do this, click on materials, because we want to go step by step. In the materials we find all the materials are concrete, which is okay. Now you go to the specifications. Now as per the specification we need to define the crack section for the beam and the columns. Though it is not important for this particular video, but it's a habit, we should do this. Okay, in the design especially. So click on beams and click on property reduction factors. So remember I told you that we should apply the property reduction factors in the horizontal direction, that is the x and the z. So let's define 0.7 moment of inertia for the columns, and again same step will repeat. Property reduction factors of, let's just here in the x direction 0.35 and 0.35 for the beams, and click on add. Okay, so for the column property go to select and parallel to y, and then assign and yes. For this property click anywhere else just to escape from this particular command, parallel to x and parallel to z, and then assign and yes. So this part is done. So then we go to supports and click on create supports. So we create a fixed support here, and here we go to the front view. So going to the front view, just click here and press Shift+1, you go to the front view here and select this and assign and yes. So you go to view now, and you go to the isometric view to see the supports assigned. Now you go to the loading here, and we go to the definitions. So this is the most important part, and here seismic definitions, we add the seismic definition here. And first of all you need to select your code. So our latest code which is available here is 1892/2016, and then click on generate. Wait for some time, and first of all we'll go with zone. Agartala is zone 5. So you can see zone factor automatically the software takes. So if you take the seismic special moment resisting frame, the response reaction factor the software automatically takes. And our building is in all other buildings, so it will other buildings, so the importance factor is 1, and the soil type is medium stiff, and the structure type is all other buildings. Okay, so it is all other buildings because as per the IS code we have selected this all other buildings because our building doesn't contain any brickwork. Okay, so we have to select this particular option, all other buildings. Damping ratio is 5%. Now we had calculated the time period in x and z direction. We'll let the program calculate, and we'll see whether our calculation matches with this or not. By the way, you can also insert your calculation directly here. Okay, if you do not insert the calculation directly here, you will get two warnings. You will get warnings. one for X and one for Z. So in our structure we will get two warnings, but we'll check out with our calculation, so this two warnings can be ignored. So we'll click on generate and click on add. Then we'll add the floor weight. We'll not ignore the self weight here because we are not considered self weight where manual calculations. So directly we'll go to the floor weight. So since this is in the seismic load, so there will be no negative sign. So first of all, it is 12 for the typical floors, and you can just use the node tools and utilities, sorry, and node to node tools, node to node distance. You can see the node to node distance here 1.95, 3 and 3 and 3, and you can see this from this floor to this floor the height is 7.95. so if you just do 1 to 8, then all 1, 2, 3 floors will be covered. So minimum 1 and maximum 8, then all the floors will be covered here, and then click on add. Okay, so similarly for the live load here, you will apply live load of 3 which you had calculated. Okay, so live load of 3 will be added in this same range, but in live load you need to apply factor. So 3 multiplied by 0.25, which comes as 0.75, will be applied here. So we'll click on add here in the seismic weight. So now comes the terrace floor. For the terrace floor, the dead load is 10, and the range for the dead load will start after 7.95. So if we just do minimum range, 8.2, okay, and the maximum range, let's do 12, okay, and the pressure is 10. Click on add. Now for the live load in the terrace, as per the IS code, we know that there will be no live load consideration in the terrace portion, so we'll just cut this. Okay, so then we'll go to load case details and click on add. First of all, we'll add the seismic loads, and I'll name it SLX, and then click on add, and then similarly SLY. By habit I didn't add the vertical one, so SLZ, and then click on add. So these three are added. So now click on add, and in here we'll go to seismic load X direction factor 1, add and close. Similarly we go with the Y direction and the seismic loads and Y direction factor of 1, and then we'll close this seismic load in the Z direction. So click on the seismic load Z direction factor 1, click on add and close. So these three have been added here, and now we need to make some correction in the STAAD editor so that we don't produce any warnings here. So you can see there are two errors here. So we'll see these errors later. First of all, let me just go here in the utilities and see what is the finish command. Floor finish command obviously we didn't give, and analysis command we didn't give, so I didn't complete the design, that's why the error has come. But first of all, let me just complete one thing. We'll go to utilities and click on the command file. So the command file will appear below. We'll just control plus move your mouse to zoom in, okay, just to show you. And in here we'll go out to our this. So in this we'll just add perform analysis, and then we'll add change. So this is done to avoid one error here, and we'll copy this one, and after all the seismic loads we'll add this, okay, and press Ctrl plus S and close. So after this we'll go to analysis and design, analysis commands, add all, add and close, and then we'll go to analysis and design and run analysis. Now let's see if we have any warnings other than the two warnings which I told you. Okay, you can see there are two warnings. So you can see the output file. The two warnings will be for the time period, but you can see, I'll just zoom in this particular value, and you can see the base dimension is calculated lowest support. This is for the error for the time period, but we'll as I told you, we'll verify the time period. Okay, so don't need to worry about this. So base shear, first of all, let me just zoom in here. So now base shear, we have three base shear here, X, Y and Z. First of all, let's look for the X. Just click here, X. Now first of all, we'll verify the time period. Our time period is 0.22, in the Excel file, we can verify that. You'll see our time period in the X direction was 0.22 and 0.3323 in the Z direction. So 0.22 in the X direction, and in Z direction it is 0.23. So it matches exactly. Now next thing we need to match is the seismic weight, whether we calculate the seismic weight correctly or not. It is 17370. Okay, so let's see our Excel file, which is what is our base seismic weight 17370. So exactly it matches, so there is no error. So and then it comes and then we have this particular factor 0.09 for the horizontal directions. Okay, so let's see what are the factor we have taken for the horizontal direction. We have taken 0.09. So exactly the same value we are getting here for the base shear 1563.30, 1563.30, and for the Y direction we are getting the exact same value 1042.20, and you can see here 1042.20, and for the Z direction obviously it is again 1563.30. so the base shear matches exactly with the value which we have calculated. So if you like this kind of videos on the seismic loading to clear your concepts, make sure you comment below and drop a like for supporting this. Thanks for watching. Bye bye.